We are solving question number 32 of GATE 2013 chemical engineering paper. And the question is, water with a density of 1000 kg per meter cube is flowing through a nozzle as shown below and exiting to the atmosphere. The relationship between the diameters of the nozzle at locations 1 and 2 is d1 is equal to 4 times d2. The average velocity of the stream at location 2 is 16 meter per second, and the friction loss between location 1 and location 2 is 1000 Pascal. Assuming steady state and turbulent flow, the gauge pressure in Pascal at location 1 is dash. So in this question, we have been given a nozzle through which water is flowing with a density of 1000 kg per meter cube. So at this location 1, the diameter is d1, and at location 2, the diameter is d2. The average velocity of the stream at location 2 is 16 meter per second square. That has been given. And the friction loss between location 1 and location 2 is 1000 Pascal. So friction loss, we can write it as 10,000 Pascal between 1 and 2. So we have been given a turbulent flow and have been asked to find the gauge pressure at location 1. So we can use the Bernoulli's theorem to find the pressure at this first point, and then we can just change it to gauge pressure. So according to the Bernoulli's theorem that is obtained from the energy conservation, we can write this Bernoulli's theorem as P2 minus P1 upon rho plus rho H2 minus H1 plus 1 upon 2 alpha, where alpha is factor accounting for turbulent or laminar flow, V2 square minus V1 square plus summation of all the forces of the friction losses plus the work done. This will all be equal to 0. So over here in this question, we are not gaining any elevation while the fluid is being transported. That is, no height gain is observed. So we can equate the second term as 0. Similarly, no shaft work is done on this fluid in order to transport it to other level. So we can say that shaft work is also 0. Then this summation of F, we can write it as this friction loss. Now, ultimately, we have to find this value of P1. And the other thing that we don't have in this over here is this value of V1. So we can find the velocity of V1 by using the equation of continuity. So from the equation of continuity, we can write that rho1 A1 V1 is equal to rho2 A2 V2. The density of the fluid will remain the same since it is an incompressible fluid. So we can cancel this term. The area at this point, location 1, is pi by 4 d1 square. Velocity we have to find as v1. Area at this point is pi by 4 d2 square, and the velocity we have been given as 16. So this will get cancelled out, and v1 will be d2 upon d1 whole square into 16 square. So over here we have been given that d1 is 4 times of d2. That implies d2 upon d1 will be 1 upon 4. So it will become 1 upon 4 whole square into over here we are only having velocity, so this is not square, this is also not square, into 16. So V1 will be 1 upon 16 times of 16, that is 1 meter per second square. So V1 we obtained it as 1 meter per second. Now other thing that we have to find is friction losses. So over here we have been given that the friction loss between location 1 and location 2 is 1000 Pascal. So that is, we can write the friction loss in terms of this P by rho as 10,000 upon rho, that we can write. So now we will replace the value of V1 and this friction loss in this equation, and then find the value of this absolute pressure at P1. So that will become P2 minus P1 upon rho plus half times of 1 upon 2 alpha V2 square minus V1 square plus F we found out as 10,000 upon rho is equal to 0. Now we can replace all the values over here. So P2 we haven't been given anything about this P2 minus P1. So we can write this as P1 minus P2 is equal to 1 upon 2 alpha rho V2 square minus V1 square plus 10,000. Since we have been given turbulent flow, that implies alpha will be 1. Then we can replace the values of density. Rho is 1000, V2 is 16, and V1 was 1 plus 10,000. So this will become 256 minus 1 is 255. 255,000 upon 2 plus 10,000. So we will be having P1 minus P2 as 137500. Now we have to find the value of P1 gauge pressure, and these are ultimately we can say these are the absolute pressure. So that we can also write it as P1 gauge minus P2 gauge is equal to 137500. Now if we look at this second point, that is P2 gauge, it will be P absolute minus P atmospheric. Now since at this location 2 the fluid is already exiting to the atmosphere, the pressure at this point will be equal to P atmospheric. So this P2 gauge will be equal to P atmospheric minus P ATM is equal to, it will become 0. That is, we can write as P1 gauge will be simply equal to 137500. So the final answer, we can write it as 137500.